今日の座長を高木俊介先生にお願いしております。
どうもよろしくお願いします。Okay. Today's colloquium speaker is Professor Mircea Mustaţă from University of Michigan. He was born in Romania and he completed his PhD in UC Berkeley in 2001. And after that, he got a prestigious research fellowship from Clay Institute, and he joined the University of Michigan in 2004. And then, he quickly became full professor there. Professor Mustaţă was an invited speaker of International Congress of Mathematics, ICM, in 2014 in Seoul, and his research focuses on algebraic geometry, especially in particular, singularity of algebraic varieties, which plays an important role in higher dimensional algebraic varieties. And today, he will talk about an important invariant of singularity called minimal exponent. So the title of his talk is Minimal Exponent of Hypersurface Singularities.
Okay.
Please.
All right. Thank you very much for the kind introduction. And thanks so much for the invitation to give this talk. It's an honor to be here. So what I want to do, I want to give an overview of this invariant of singularities. And probably what I'll do, I'll focus mostly on some open questions that I think are actually quite interesting. But I'll start, first of all, let me set up the notation. So everything for the sake of clarity, so I'll just work in the affine space in Cn. So I want to understand basically polynomial, the singularities of such an object. I'll assume that it's non-constant to avoid trivialities, and whenever things will come up, basically I'll think of the corresponding hypersurface consisting of all the zero locus of F. Okay, but I want to start with actually with a very old story, which is about something called complex powers. So this goes back to a question of Gelfand from '54. So here is the setup. So let me say a little bit about the complex powers of F. So this is a function which is defined on the half plane of complex numbers whose real part is positive, and which takes value into distributions. So distributions on Cn in such a way that it maps an S, right? So it's a distribution, so it associates to every function, every smooth function with complex support, the following integral. So integral over Cn of the absolute value of f of z to the power 2s times phi of z dz bar. And it's actually quite elementary to check that this is well defined in this half plane, and also it is holomorphic. All right, so if you want, for every fixed function phi, I get a holomorphic function. And Gelfand asked at the ICM so this was Israel Gelfand in '54, asked to prove that, so a question, so is this, can be this extended meromorphically to C? Meromorphic on C. Okay, there is one case that's actually very easy to do, which is the case of a monomial. Right, so suppose that if I have f to be x1 to a1, xn to an, right? So what you do is, first of all, I'll always treat basically, right? So the absolute value of f of z to the 2s, I'll think of it as f of z to the s times f of z bar with s. Right, and if I basically I want to do integration by parts, right? So this basically what I have here, maybe I won't write everything. So basically what I have to deal with xi to the ai, or let's say zi, maybe let me put these z's. So I have to deal with zi to the ai times s. So basically what I'm going to do, I'm going to multiply by ai s plus 1, right? And then you do integration by parts. Of course, the derivative with respect to zi does not affect the anti-holomorphic part. So basically, phi has complex support. So if I go far from the origin, I just get 0. So basically, integration by parts allows me to move from, instead of zi to ais, basically I move to zi to the ai s plus 1 at the price of basically replacing phi by another smooth function with complex support. Right? And now you see, basically what I gained out of this is that instead of this to be defined on the real part of s positive, I define it when the real part of s is larger than -1 over ai. Right? And then you iterate. Of course, you do the same thing for the anti-holomorphic part. So you iterate. So what you get, okay, maybe I'll move here and I'll leave this to change. So if I iterate, what you get meromorphic continuation such that all poles of the form something like minus k over ai for some positive integer k. Okay? And I think Gelfand actually and Shilov actually, they worked a lot on this, on expanding this very naive computation to a lot of functions. But then the complete solution actually took quite a bit to come up. So there were essentially, first of all, two solutions around 70. So they were given in two different papers, one by Atiyah, the other one by the other Gelfand, Sergei Gelfand, and Bernstein. So what happened around this year, a few years back, is that Hironaka proved his resolution of singularities. Right, so this solution, so this uses Hironaka's resolution of singularities. Okay, so let me tell you what this does for us. Right, so I'll write in a second. The idea is that you go to another model, to another manifold, on which the function becomes a monomial locally, and also the determinant of the Jacobian is given by a monomial. Right? So if you want to change a variable formula, it's important to control also the determinant of the Jacobian. Right? So this implies the following, that you get some map from y to, again, to Cn. Let's say this is pi. Pi is proper, if you want, in the sense of usual topological sense. The inverse image of a compact is compact. So y is a manifold, a smooth manifold. And this is also, it's an isomorphism, it's a diffeomorphism outside the measure 0 subset. And the important condition is that on y, we have local coordinates. Let's say y1, right? Around every point I have some coordinates such that the pullback f of pi of y is given by some invertible function, which does not matter for our purpose, times y1 to a1, yn to an. And similarly, the determinant of the Jacobian of pi is given by v from y1 to k1, yn to kn. And again, u and v are invertible and can be ignored. Okay, and then if you use the change of variable formula, the integral downstairs becomes an integral upstairs. And the moral is that you have to deal with expressions that look like product of yi to the power ais plus ki. Right, but then you play exactly the same game that I've done before. Right, so basically now you multiply by something that looks like ais plus ki plus 1 and so on. Right, so you can, so the similar argument implies you get meromorphic continuation. And you get also an interesting statement about the poles. So every pole is of the form minus ki plus m over ai for some positive integer n. Okay? And furthermore, in fact, you can say a little bit more precise, right? So it's clear that from this formula, what is the largest possible pole, right? But in fact, it turns out that that candidate is the largest pole. In fact, the largest pole is the negative of, right? So what you get basically, what I have to do, I have to take here m to be 1 is the minimal value, right? And I have to minimize over all such things. Right? So by the way, here when I write like this, I mean that there is some chart on y and there is some I with this property. Right? So this is, the largest pole is the minus the negative of this ki plus 1 over ai over all I, meaning over all charts. And this has become known afterwards, especially in birational geometry, as the low canonical threshold of F. So actually, it got this name quite a bit later. All right. So this is the first solution which was given in these two papers, and then there was another solution just a couple of years later. Due to Bernstein. So Bernstein wrote a paper developing the algebraic theory of D-modules on the affine space in order to prove this result. So what he showed is that you don't have to go to a resolution of singularities in order to run this integration by parts argument. You can do it downstairs. So what he showed is that there is a polynomial. So there is a non-zero polynomial B of S such that you can write B of S times F to the S as some differential operator. So this is something involving the S, also X and partial X, but applied to the symbol F to the S plus 1. Right, and this you can take algebraically as a purely formal symbol in which F to the S is just a symbol on which you know how to apply differential operators. But in fact, in our setting, in which for us F to the S is this distribution, this has the usual, I mean, the intended meaning. And you see then what you have to do is I have this absolute value of F to the power 2S, which is F to the S times F bar to the S. I just multiply by B of S and B bar to the S, and I do exactly the same argument then. So again, so once you have this, then can, maybe before doing that, let me just introduce one piece of notation. So of course there are many such polynomials. They form an ideal in the polynomial ring in one variable. So the minimal, the monic polynomial of minimal degree with this property. Is what's called the Bernstein-Sato polynomial, or the B function. So I'll write it as BF of S. Okay, so it appeared a few years earlier in the work of Sato. All right, so if you run the same argument, so what you get again that there is a meromorphic continuation, and you can say again something about the roots. Again, so what you have to do in this setting, you first multiply by B of S. So this allows you to go from real part of S positive to real part of S larger than -1. Then you multiply with B of S plus 1 and so on. So what this tells you is that every root of BF, every pole of ZF is of the form lambda minus m, where BF of lambda is 0 and m is some non-negative integer. Okay? So this gives another proof somehow without having to go, in some sense it's more intrinsic. You don't have to go through resolution of singularities. And now if you compare, right, so basically you have two estimates for the poles. So there are the ones which say that they are of this form in terms of a resolution of singularities, and there are these ones in terms of the roots of the B function, which are more intrinsic. So this suggests some sort of relation between these roots, and in fact it's a very important theorem due to Kashiwara and then improved by Lichtin. So this says that all roots of BF are negative rational numbers. And in fact, you can say more precisely in terms of this resolution. Given a resolution pi, they are of the form minus ki plus m over ai for some I and some positive integer. Okay, so it's an important result that they are all rational numbers, and in fact, you don't really get an explicit description of what they are in terms of the resolution, but you get some estimate. Right? So it's not like for this invariant that I mentioned before, this low canonical threshold, you have an explicit formula, but for the other ones, you just get an approximation. But still, if you combine them, right? So I have this meromorphic continuation where I know that all the poles are of the form lambda minus m, where lambda has to be of this form. I also know that the largest pole is this low canonical threshold, right? With this expression. So a consequence of this, so as a corollary, you get that the largest root of BF of S is minus the low canonical threshold of F. All right. So now let's move on. So of course, over the years, actually, the low canonical threshold became a very important invariant, especially in birational geometry. Right? So maybe I will certainly not attempt to say too much about this. But I have to say a little bit of LCT of F. Right? So one issue is that one can drop the assumption that I work in affine space or inside the smooth variety, and basically I can allow mild singularities in the variety. And then one can work with this extension. But why is it so useful? One way to think about it, right? So in higher dimensional algebraic geometry, probably the most important theoretical tool is the famous Kawamata-Fivek vanishing theorem, right? And one way to look at it is in terms of what are called multiplier ideals. So Nadel gave a vanishing of this theorem. So there is a family of ideals called multiplier ideals that can be defined either in terms of a resolution or analytically in terms of integrability conditions. So I'll write them like this, which again measure somehow the singularities of F. And the important part is that when this hypersurface has singularities, if you want to get certain vanishing results, you have to twist by these ideals. And one way that this low canonical threshold can be interpreted is the fact that basically it measures the triviality of these ideals. So this, more precisely, you have that this ideal is trivial if and only if lambda is strictly less than the low canonical threshold of F. So in this way, if you want to apply vanishing theorems, it's very important somehow. I mean, that's what's behind to control in some fashion this invariant. From my point of view, what I really like about it is the fact that it shows up in a lot of instances related to singularities. So I'll discuss two other instances towards the end. But somehow, I think there are lots of situations in which you are led with formulas that somehow lead you to this low canonical threshold. All right, so I think that's as much as I wanted to say about it. In fact, the invariant I'm interested in is a refined version of this one. But first of all, I should tell you, first of all, unfortunately, I didn't give you any example. Right? So let me mention a couple of things. So first of all, what happens if the hypersurface Z is smooth? Right? So then I don't need to take resolution of singularities. Right? So then if you think about the formula, for example, for the low canonical threshold, there is only one, right? Basically, there is only one I for which AI is 1 and Ki is 0. Right? So in fact, so in this case, the low canonical threshold of F is equal to 1. For example, if you take, it's also useful to think about it in terms of, so let's say, for example, let's say if F is x1. So for example, what can you say about the B function, right? So then you see that you have the easy formula that s plus 1 times x1 to the s is dx1 times applied to x1 to the s plus 1, right? Which I guess shows that at least s plus 1 satisfies the property of in the definition of this B function. Right? So this, I guess this does not quite prove that it is this one, but it implies that Bf of s divides s plus 1. So the other remark to make is that in general, this is the best behavior from the point of view of the low canonical threshold, in the sense that the low canonical threshold is always less or equal than 1. Right? And in fact, being equal to 1 bears an important name, so it's called low canonical singularities, and that plays an important role in higher dimensional algebraic geometry. But now, for now, let me just mention another one remark, which is that -1 is always a root. So Bf of -1 is always 0. So in particular, in this smooth case, Bf of s has to be s plus 1. Right? And this is because, I don't know if I still have the definition of this B function. I don't think so. So you see, so I know that Bf of s times f to the s is some differential operator applied to f to the s plus 1. right? But then I can specialize S to -1. So what I get that BF of -1 times 1 over F is some differential operator applied to F to the S plus 1. So now this becomes just 1, right? So this is, I don't know what it is, but it's just some polynomial. Okay, but of course I assume that F is not constant. So this implies that BF of -1 is equal to 0. So that's another, the fact that BF of -1 is 0. So this means that there is a root that is -1, which is one way to think of the fact that the low canonical threshold is always bounded above by -1, right? Because remember that the negative of the low canonical threshold was the largest root. Okay, so here is the main object that I want to talk about today. So this was defined by Morihiko Saito. So the minimal exponent alpha tilde of F is the negative of the largest root. So basically I'm getting rid of this -1. Negative of the largest root of BF of S over S plus 1. Okay? So there is one case to treat separately, right? So there is a possibility that this BF of S over S plus 1 is just 1, as in the smooth case, right? So the convention, so this is infinity if BF of S is S plus 1. And in fact, one can show it's not entirely trivial. So this is equivalent with the fact that Z is smooth. All right, so this is the invariance. Maybe, right, so if you remember that the largest root of BF of S is the negative of the low canonical threshold, and also if the negative of the largest root of the B function over S plus 1 is this minimal exponent, it follows that. So note that the low canonical threshold of F is the minimum between alpha tilde of F, between the minimal exponent and 1. Okay? So in some sense, this minimal exponent gives interesting information precisely when the low canonical threshold stops being interesting, which is when the low canonical threshold is 1. Okay? And the fact that you already see something interesting just by asking when the minimal exponent is different from the low canonical threshold. So this is the theorem of Saito. So this is in the paper in which he introduced this invariant. So he showed that alpha tilde of F is in fact larger than 1 if and only if the hypersurface Z satisfies the condition known as has rational singularities. Okay, so this I think shows that somehow this gives interesting information, and in some sense one can think of this minimal exponent precisely as giving some sort of numerical measure of rational singularities. Okay, and let me give one example. So say if F is x1 to a1 plus xn to an, then this minimal exponent of F is 1 over a1 plus 1 over an. And of course, I want it not to be smooth, so I'll assume that all the AIs are at least 2. Okay? All right. So again, so this is the definition that comes out of D-module theory. So in terms of this invariant, which is quite subtle, this B function associated to F. So classically, I guess in the 80s, the invariant was very much studied for isolated singularities. So I will not say too much about it, but let me just mention the definition in that setting, because somehow, I mean, just to give a feeling for what was involved. In fact, the definition in that setting is much more analytic. So alpha tilde of f was studied in the 80s, sometimes under the name of Arnold exponent, by people like Varchenko, especially, and Steenbrink, and Lozer, and so on. For when, let's say, f equals 0 has an isolated singularity. Let's say just at 0, right? What this means, right? So it means that f of 0 is 0, and right, and outside of the origin, there are no other singularities. So another way of saying it, so if you look at the dimension over C of C x1 over xn over the partials df mod dx1 df mod dxn in the neighborhood of 0, so this is finite. Okay, so here's the definition in that case. And in fact, a lot of properties were proved using analytic methods in the 80s by these people. So the definition involved integrals over vanishing cycles. So the definition was the following. So I will not go into all the details. So the idea was the following. So you look, so you have around the origin, you know that you have isolated singularities, which means that if I look at f inverse of t in some small ball around the origin, so by Milnor's work, then this has the topology of a bouquet of spheres. So this means that you have cohomology just in middle dimension, and then I'll take some gamma of t, and right, so this is of dimension n-1, so this is an n-1 cycle. And you integrate over gamma of t, so I'll take some auxiliary function g times an n-1 form, which will be this d z1 dzn over df. In other words, it's any n-1 form that wedged with df gives dz1 dzn. And what one can show is that this has an asymptotic expansion when t goes to 0, which looks like sum, and you get some coefficients. So this is the sum over, let's say, alpha and k. So I get some coefficients that depend, of course, on all the data. So depend on g, they depend on this cycle, gamma, they depend on alpha and k, and you have t to the alpha times log t to the k. Okay, and what the minimal exponent is, so alpha is always greater or equal than alpha is larger than -1, and in fact this minimal exponent is 1 plus the smallest alpha that appears in such a development, in such an expansion. Okay, so this is the object that people were interested in, and which is related with what's called the mixed Hodge structure on the cohomology of the Milnor fiber. And the fact that actually the definition of the minimal exponent that I gave before coincides with this one. I think that this is a result due to Malgrange. Okay? All right, so I think I'll stop here with this general introduction. So what I think is very interesting is to try somehow to build on the theories that we know about low canonical thresholds and see what it gives in the setting of this more refined invariant. Right? So basically there are two possibilities. One is to try to prove properties of the low canonical threshold for this minimal exponent, and I think that basically we made progress on that part. So I think that the main such properties are known. And the other, maybe more interesting thing would be to extend the connections between the low canonical threshold and various points of view on singularities to this minimal exponent. And this is maybe what I'll try to stress more. But let me just say a few words about what we can do at this point. So the goal is to extend properties and characterization of LCT to this minimal exponent. So in one direction about properties, so recently Mihnea, Popa, and I, basically we extended, so we proved some of the main properties of this alpha f, of alpha tilde of f, that parallel corresponding properties of the low canonical threshold, such as semi-continuity in families, or behavior under restriction, to, let's say, for example, you take what I mean is something like f restricted to xn equals 0. Right? I want to relate the minimal exponent of f with the minimal exponent of this restriction to a hypersurface. And it's very easy to see what you expect to be true, right? So remember that this, like the low canonical threshold, this invariant is large if the singularities are good. So for example, what sort of semi-continuity you expect is that if I have a family, right, whenever I go to a special fiber, then actually the singularity should get worse, so the invariant should go only down. It cannot go strictly up. When I cut with the hyperplane, again, the singularity should get worse, so they should not be larger than the ones that I started with, at least in the neighborhood of that hyperplane. Right? So I just want to say a couple of words about the method that we used. So what was involved was a generalization of this theory of multiplier ideals using Saito's theory, Morihiko Saito's theory of mixed Hodge modules. So this used let me say directly the Hodge filtration on the localization Rf. So here R, let me remind you, so it's a polynomial ring, right? So Saito's theory of Hodge modules basically endows certain modules over differential operators with more structure. So in particular, on this localization, which comes from the complement of this hypersurface, there is a certain filtration given by Hodge modules here. Okay, so Saito constructed this filtration. So I will not try to say what it is, but basically so these are some submodules over R, right? So I can multiply with R. They are compatible with the action of differential operators. But what's known is that this lies inside 1 over f to the p plus 1 times Rf. Well, so there is another naive filtration, what's called the pole order filtration on Rf. And then you can measure the difference between these two things by writing the first part as an ideal, Ip of f times what's on the right-hand side, 1 over f to the p plus 1 times Rf. Right? In other words, you multiply this guy by f to the p plus 1. So this is what I refer to as Hodge ideal. So they are really analogs of multiplier ideals. So in fact, when p is equal to 0, you get exactly one important multiplier ideal. So you get I0 of f is what I wrote before as this multiplier ideal. Okay, and more generally, one can consider Hodge filtration on things that look like Rf times symbol like f to the minus alpha. This also comes with a Hodge filtration, and you get ideals that look like this. Okay, and the upshot is that, so the key point is that the minimal exponent alpha tilde of f is greater or equal than p plus alpha, where this p is some integer and alpha is a rational number in between 0 and 1, if and only if Ip of f to the alpha is trivial. So again, it does not really matter so much what these ideals are. So the point is that by building on this theory, you prove that the ideals satisfy various formal properties, and then you have a characterization of this number as some sort of threshold at which the ideals become trivial. Right? So again, so you want to understand what is alpha tilde. Basically, you just ask whether it's greater or equal than some rational number. You write the rational number as p plus alpha in this form, and then you ask whether this ideal is trivial or not. Okay, so again, so this parallels very much the study of the low canonical threshold, say, using multiplier ideals and their properties. All right, so then maybe I should mention here then properties of Hodge ideals imply properties of alpha tilde. But I think what I would rather do is basically explain some open questions about the invariant and about its connections with other fields, rather than talk too much about technical results. So here are a few questions. So maybe one that somehow feels like one should be doable concerns the analytic characterization of the minimal exponent. Okay, so conjecturally the following picture should be true. Well, so note, first of all, one remark, that ZF always has poles at negative integers with multiplicity 1. So even if you take f to be, for example, x1, then this complex power still has poles. And the assertion is that, so the question is the largest non-trivial pole So of course, by non-trivial pole, I mean I get rid of these poles with multiplicity 1, and I look at the largest that still exists, the largest non-trivial pole equal to minus alpha tilde of f. So the answer is yes, if f has isolated singularities. So this is a result from the 80s due to Mircea. But somehow, I don't think that we can do the general case yet. For example, it's easy to see that the largest non-trivial pole has to be less or equal than this minus alpha tilde of f. But to show that it's really minus alpha tilde of f, you have to actually give a function, compute something, and show that you indeed get a pole over there. Okay? All right, so the second question I'll ask is, actually, I'll leave rather vague. So this is a description of alpha tilde of f via divisor over Cn, in the same way that you describe the low canonical threshold as the minimum of those quotients. I will not say too much because this will get a bit technical. So basically what I would like somehow to write again alpha tilde of f as the minimum of certain quotients, like the low canonical thresholds, for certain divisors E. But it's not clear what those divisors should be. All right, so maybe the most interesting questions are 3 and 4 that I'll talk about. So this is, again, so this refers to two connections between the low canonical threshold and other points of view on singularity. So this concerns the characterization via p-adic or motivic zeta functions. Okay, so let me maybe explain briefly what is this p-adic zeta function. Right? So suppose that f now, instead of having complex coefficients, has integer coefficients. And I choose, so of course it's not a constant, and I choose p to be prime. Okay, so in this case there is a p-adic version of the complex powers. In this case, you don't need to think of it as a distribution. It's simpler to just write z of s. So this will be just a value. So this will be an integral over zp to the n of the absolute value of f of x to the power s. So this is the p-adic absolute value times d mu x mu p. Right? So this is the Haar measure on zp to the n. Okay, so what does it actually mean? Let's see, maybe I should still use this one. All right, so one observation is, first of all, what is this p-adic absolute value? All right, so basically this is 1 over p to the order of p in f of x, right? Because you have to take the p-adic absolute value of f of x. So note, so the p-adic absolute value of p is 1 over p to the power whatever power p appears in U. Right? So what this means is that, so what does that integral do? Right? Basically, I have to apply f to various p-adic numbers, and I have to figure out what is the largest exponent of p in that number. So that this implies that, in fact, understanding ZFP is just equivalent with understanding the behavior, understanding actually the number of all u's in z mod p to the mz to the n, such that f of u is equal to 0. Right? So basically, you compute roots of f modulo p to the m for all n. Right? It's just a way to package this information. So the other comment is that, so before we saw that this complex power is meromorphic. In this case, this is also meromorphic, but in fact, it's something much stronger. So this is a result of Iguza, and then reproved also by Denef, so which says that ZFP is a rational function in 1 over p to the power s. All right, and in fact, you can also say what the poles are, and the poles, and let me say in terms of a resolution of singularities. Every pole. Well, so these are not rational numbers because, right, it's in 1 over p to the power s, but basically, I'll just talk about the real parts. Every pole, let's say S0, has the real part of S0 being minus one of those numbers that showed up, minus K1, Ki plus 1 over Ai. But note that in this case, I don't allow increasing the numerator. Right? So this is really one of the quotients that, for example, appeared in the definition of the low canonical threshold. So this is what Iguza proved, essentially following the idea of the first proof of the fact that the complex power is can be extended meromorphically. Probably what I should have said is that this is defined also when the real part of S is positive. So let me just put here the real part of S is positive. Okay? All right, so that's the story. And then the most famous conjecture in this area, which is still extremely mysterious, it's attributed to Iguza, but all the experts say that actually Iguza did a lot of computations, but he never stated it in print. So this says that but I'll still attribute it to Iguza. So every pole S0 of ZF satisfies so its real part is the root of the B function. Okay? All right, so now let me go to minimal exponents, and the question is the following. So this is motivated, if you want, also by the result of Lezers that's known for isolated singularities in the Archimedean setting. So is the largest non-trivial, maybe I should have said, okay. So the largest pole is always known to set, I mean, the largest real part of a pole is always known to be minus the low canonical threshold. So here I mean that is the largest non-trivial pole. Basically, I get rid of minus 1 if the largest, okay, I should, real part, the largest real part of a equal to minus alpha tilde of f. So this, I think, would be extremely interesting to understand because somehow might give some insight in the general case of the monodromy conjecture. Okay? All right, and I guess I should end up soon. So let me go to what I think is actually the most interesting aspect, and which is somehow very much open. So connection, positive or mixed characteristic. Okay, so let me remind you that there is a very rich theory of singularities in positive characteristic, right? So which somehow, I mean, provides some very interesting parallel to the story in characteristic 0, and it interacts with it in a very subtle way, right? So let me just recall here. So there is a, so let me start again. So let's say now again that I assume that f has integer coefficients, and I'll reduce mod p. So this will lie over z mod pz. So in this case, there is a very interesting analog of the law canonical threshold that was introduced by Takagi and Watanabe. So this is an analog of LCT. So this is this F pure threshold of Fp. That has nothing to do with the resolution of singularities, right? So which, roughly speaking, which encodes basically which powers, which Fp to the I belong to. So let's say I look just around the origin to x, the ideal x1 to the p to the e, xn to the p to the e. So somehow the idea is you make explicit use of the Frobenius morphism, right? So let's say, again, I'm just working around 0. And again, it's not just that you have this invariant. The interesting part is that there is a lot that can be said. For example, there are analogs of multiplier ideals called test ideals. Maybe I won't say much about that, but for example, there is a very interesting set of results that I think are due in various settings to maybe Hara, Takagi, Watanabe, and Yoshida, which does the following. So if I take, so let's say I reduce, so let P be large enough. In fact, so what's known is that the law canonical threshold of F is greater or equal than the F pure threshold of Fp. It's also known that the limit when P goes to infinity of the F pure threshold of Fp is the law canonical threshold of F. And maybe the most interesting question here is that are there infinitely many P, or maybe a set of positive density, such that in fact you have such that the law canonical threshold of F is equal to Fpt of Fp. Okay, so this is actually a very interesting question that somehow has connections to the ordinarity conjecture in arithmetic geometry, and somehow it would be extremely interesting to say something. But this is kind of a side remark. So basically, for me, the main question is how to put what is the analog of alpha tilde of F in characteristic P. Okay, this is not like an empty question in the sense that, so there's been recently some progress. So basically the main thing that shows that actually there is such a theory by Christopher Dodd. All right, so he showed the following. So maybe I'll just explain his statement. I mean, it's not particularly important what the statement is, but just to give the flavor. So suppose let P be large enough. So then what he says is that, and T, okay, to make it precise, again, just ignore this. T is the negative of the smallest integer root of Bf. So again, just ignore this. And let's, for each m, so let's say that Fm, let Fm bar belongs to this, maybe I'll just say F bar, Fp bar. So this lies in Z mod P to the mz of x1 over xn. All right, so the assertion is the following. So that you have alpha tilde of P greater or equal than, let me put here m plus 1. Alpha tilde of P is greater or equal than m plus 1. If and only if you have a condition at the level of differential operators, but in this ring, modulo P to the m plus 1, which says that F bar, like P to the m plus 1 minus m plus 1 times P lies in the what you get generated over this. Okay, let's say, let me introduce also this. Let's say this is R bar. In R bar of D1 dn and times F bar to the power P to the m plus 1 minus TP. Okay, so again, it's really not important what exactly the statement is, but basically what it says is that by reducing, and this time you don't reduce just mod P, you have to reduce modulo higher powers of P, you can recover, I mean, basically what Dodd showed is that you can recover Saito's filtration on RF. And then you just translate this statement in this fashion. But again, this is just a statement that basically recovers the invariant incharacteristic 0. What I think it shows is that there should be a rich theory that you develop just modulo P to the m that somehow should give some interesting analogs of this in this setting. So let me stop here. Thank you very much.